Question 9, Part A. A particle is initially at rest at the origin. Its acceleration as a function of time, t, is given by x double dot equals 4 sine 2t. Part 1. Show that the velocity of the particle is given by x dot equals 2 minus 2 cos 2t. The velocity x dot is equal to the integral of the acceleration x double dot with respect to time. So x dot is equal to the integral of 4 sine 2t dt, which equals 4 times negative cos 2t divided by the derivative of 2t, so we're dividing that by 2, which equals negative 2 cos 2t plus the constant of integration c, which we will need to find. And we find that by applying the boundary condition that the particle is initially at rest. In other words, the velocity is 0 when t is equal to 0. So 0 is equal to negative 2 cos of 0 plus c. Now negative 2 cos 0 is negative 2, so 0 is equal to negative 2 plus c, so c is equal to 2. Therefore, the velocity x dot is equal to 2 minus 2 cos 2t as required. Part 2. Sketch the graph of the velocity for t greater than or equal to 0 and less than or equal to 2 pi, and determine the time at which the particle first comes to rest after t equals 0. Let's analyze the velocity equation x dot equals 2 minus 2 times cos 2t. Let's start with the base curve x dot equals cos t and see what happens when we multiply the t by 2, then multiply the cos 2t by 2, then multiply it by negative 1, and then add 2 to the whole thing. So multiplying the t by 2 will change the period of cos t from 2 pi to pi. In other words, the width of one full cycle is pi radians rather than 2 pi radians. Another way to look at it is multiplying the t by 2 means we get 2 full cycles of the cos curve in 2 pi radians rather than one full cycle. Now multiplying the cos 2t by 2 will stretch or dilate the amplitude by 2. So rather than the cos curve swinging from negative 1 to positive 1 back to negative 1 and so on, it's going to swing from negative 2 to positive 2 back to negative 2 and so on. Now multiplying 2 cos 2t by negative 1, which is what this negative here does, reflects the curve in the x-axis. In other words, turns it upside down. And finally, adding 2 to the whole thing translates the curve 2 units up. In other words, the line of center is now y or x dot equals 2 rather than on the x-axis. And the following graph is produced. So this is the graph of x dot equals 2 minus 2 cos 2t. Notice 2 full cycles from t equals 0 to t equals 2 pi. Notice where the peaks and troughs occur. So the minimum values are at 0, pi and 2 pi, and the maximum values are at pi over 2 and at 3 pi over 2. And from the graph, the particle first comes to rest at t equals pi. Part 3. Find the distance travelled by the particle between t equals 0 and the time at which the particle first comes to rest after t equals 0. From part 2, the time that the particle first comes to rest after time t equals 0 is at time t equals pi. Now it helps to note that the velocity is greater than or equal to 0 and less than or equal to 4, and we saw that in the graph in part 2. It's not so important that the fact that the velocity is less than or equal to 4, but what is important is that the velocity is never negative. This means that the particle never moves backwards, and this also means that the distance is equivalent to the displacement in this context. So all we need to do is to differentiate the velocity equation from time t equals 0 to t equals pi. So the displacement or the distance x is equal to the integral of 2 minus 2 cos 2t dt from t equals 0 to t equals pi. Performing the integration, we get 2t minus sine 2t from t equals 0 to t equals pi. Applying the limits of integration, we get 2 pi minus sine 2 pi in brackets minus 0. Now sine 2 pi is equal to 0. So this evaluates to 2 pi. Therefore, the particle travels a distance of 2 pi units from t equals 0 to the time it first comes to rest.